this video, we're going to discuss rational functions. So let's start by defining what a rational function is. A rational function is a function of the form f of x is equal to p of x over q of x. Well, where p of x and q of x, specifically the numerator and denominator, are polynomials. So all of the requirements we have for a polynomial, the numerator and denominator individually have to meet those requirements. And also because we've now taken polynomials where there are no issues with the domain and we've created an expression that has a denominator, we also have to make sure that that denominator is not equal to 0. Now, normally when you talk about denominators, the denominator is not 0. You kind of just leave it at that. If the denominator is 0, it's undefined. We're going to talk a little bit more now about what happens if the denominator is 0. What's actually happening when a denominator goes to 0. We're going to talk about what that looks like, specifically what it's going to look like on a graph. If we take a function like this, what's it going to look like on the graph at locations where the denominator would be 0. Very specific things happen when the denominator is 0 or when it would be 0. So what we're going to find as we graph rational functions are these features that we refer to as asymptotes. So to better explain what an asymptote is, it may be helpful to have a picture. So if you don't already have your graphing calculator out, go ahead and get that out. We're going to use that in this section. And then you may also want to have a straight edge or a ruler of some type, something to help you with graphing a couple pages down. So what I want to do now is I want to graph a really basic rational function on the graphing calculator just to give you a sense of what the picture will look like, and we'll use this to explain some of the features we're going to see for rational functions. So I'm going to go into my graphing utility. If you've already got something in your calculator, make sure you clear it out before you do anything else. I want to graph the most basic rational function, what we call the reciprocal function. So the rule for the reciprocal function is 1 divided by our input, x or whatever. Now I'm going to graph this. Hit graph. If you don't get a picture like this, it may be a zoom issue, so double check, go to the zoom menu, and you want to zoom standard, which is option 6, or you can use the arrows to move to that. Another thing you may want to do is you may want it squared off, which means that the units, the scale on the x and y axis are going to be the same. So you can also scroll down to zoom square, and if you hit enter there, it's going to distribute the x and y axis so that the scale is the same. So notice this graph has two separate pieces. These are two separate branches. Depending on your calculator, you may see a line drawn on the y-axis or you may not. Notice that there's a boundary situation involved. So the left-hand branch, the right-hand branch, completely separate from one another, and they're divided here at the y-axis. Notice on either side of the y-axis something specific is happening. So as we approach the y-axis, otherwise known as x equals 0, from the left-hand side and follow that branch, it drops down and our graph is going down towards negative infinity. So as our x values start out negative but get really close to x equals 0, the y values then drop all the way down to negative infinity. The same kind of thing is happening on the other side. So if you approach 0 from the positive side and follow the graph, the y values blow up and get really big and go up to positive infinity. But what we would notice if we zoomed in and looked a little bit more closely at these two branches is that they never actually reach the y-axis. They're completely separated from one another by the y-axis. They're never going to touch it. They're never going to cross it. The y-axis is a boundary here that's separating these two pieces of the graph. It's technically a boundary that's kind of imaginary. It's not really part of the graph in the sense that it's like a point on the graph. It's this imaginary boundary on the coordinate plane that's breaking our graph into these two pieces. This is what we call a vertical asymptote. So a vertical asymptote is a boundary around which the graph's y values, or outputs, whatever you want to call them, approach positive infinity or negative infinity. So around that boundary, the y values are blowing up. So as our x values approach this specific value at 0, the y values either go off to positive infinity or they go off to negative infinity. Well, notice where this happened. It happened at the x value of 0. Let's think about what the actual function looks like. The function is 1 over x. And the location where we ended up with that boundary is at x equals 0. Well, if x equals 0, then our denominator would be 0. And remember, that's the issue where we have something that's undefined. Before, we've just said it's undefined, it's not part of the domain, we move on. If x were 0, that now gives us the location for this boundary, for this asymptote. So these vertical boundaries that we're going to see on pretty much every rational function, those are going to occur at any location where the function is undefined. Well, the only way a rational function is undefined is if our denominator is 0. So these vertical asymptotes are going to occur where there's an exclusion from the function's domain. In other words, we have an x value that we would attempt to plug in that would make the denominator 0. Whatever x value that is, that's going to give us a location for one of these boundaries. Now, special case, one thing we do need to keep in mind, anytime we have a rational expression, ideally we want to make sure that it's fully reduced. So in identifying these particular locations where we have an issue with the domain, we want to make sure that we first off reduce any common factors in the numerator and denominator. So we'll find exclusions from the domain given that those common factors have already been divided out. So if we have common factors, we've divided them out, anything remaining that makes that denominator 0 now represents a location where we're going to have a vertical boundary on the graph. Now, rational functions will also potentially have some horizontal boundaries that behave similarly, or possibly a diagonal boundary that looks kind of like this as well. So this function, the reciprocal function, also has a horizontal asymptote. Same thing with those two branches, but notice they're also separated above the x-axis and below the x-axis. So here, if we think of our x values as getting really, really big in the positive direction or really, really big in the negative direction, think about the y value we're approaching. We're getting really, really close to 0. So if we were to go out towards positive infinity, follow the x values as they get really, really big, that particular portion of the graph is sloping downward and it gets really, really, really close to the x-axis. Same thing on the other side. If we follow the x values as they go out towards negative infinity, that particular branch of the graph also gets really, really, really close to the x-axis, but approaching it from below. Same thing as with the y-axis though. The graph is going to get really, really, really close to the x-axis, but if we were to look further at the graph, zoom in, look a little bit more closely at what we see on the tails of the graph, we'll actually see that we never truly touch the x-axis or cross it. We get infinitely close, but we're never actually going to reach it. So this is what we call a horizontal asymptote. Same thing as vertical in terms of the way the graph behaves around it, but it happens to be a horizontal line instead. So a horizontal asymptote is a boundary that's approached as the graph's x values go towards positive infinity or negative infinity. So notice in both of these cases, we're talking about issues related to infinity to negative infinity. So when we're talking about rational functions and these specific features, it's very much related to infinite behavior. What happens as our x values get really big? What happens as our y values get really big? We have just portions of the graph that kind of just drift off and go towards particular locations in these particular ways, and the boundaries end up dividing the graph into pieces either vertically or horizontally. Now, the horizontal asymptotes are not going to be as simple to find in terms of how they're related to the function itself. So vertical asymptotes occur where the function is undefined, in other words, where we have a divide by 0 error. Horizontal ones, well, if vertical is related to our domain, Horizontal would be related to our range. We're talking about a y value. So these particular boundaries, these locations where things just go off to infinity, we get really close to a line, but we never touch it, we never cross it, they may occur at a location where there's an exclusion from the function's range, a break in the y values, but this is not always going to be the case. In other words, we don't have to have an exclusion from the range, like we have an exclusion from the domain, in order for there to be a horizontal asymptote. Now, some functions will have a slanted diagonal asymptote, but because we're talking about a diagonal line, this is going to be completely independent of domain and range. So we can still cover a bunch of x values, all of our y values, and have a slanted boundary that's going to break our graph into pieces and define the shape of the graph. Now, as we look for these asymptotes, as we start to graph, there is an important distinction we need to make. A graph cannot cross a vertical asymptote. In order to cross a vertical asymptote, it has to touch that particular x value. But remember, that x value is not part of the function's domain. It's a location where the function is undefined. Undefined in the sense that there is nothing there. So any location where we say there's a vertical asymptote, that location, that boundary, is truly going to divide the function or the function's graph into separate pieces. So once we define the locations for those vertical boundaries, we know that they're truly separating the graph into a left piece, a right piece at that location. Now, on the other hand, a graph can cross a horizontal or slanted asymptote. Sometimes it does, sometimes it doesn't, and we'll talk about how you determine whether or not it does or does not. So before we look at graphing, let's develop a little bit of notation to talk about this special behavior we're seeing with this kind of function, this rational function. So we need to talk about the idea of approaching a value. This idea that we're getting really, really close to something, but we may never actually reach it, we may never actually touch it. Just like this graph of the reciprocal function is getting really, really close to the y-axis, but it's not really going to reach it, it's not really going to touch it, it just happens to get really close. We say that it's approaching a particular location. So if we want to talk about something approaching a value, x approaching a value from the right, in other words, from the positive side of the coordinate plane, the notation for this is x approaches this value that we're calling c from the right, from the positive number. So we're going to write a superscript plus sign. Now, if we want to talk about approaching from the left, from the negative side of the x-axis, same kind of thing, but x is approaching c from the negative side. Now, we can also talk about approaching infinity and approaching negative infinity. When we say that x is approaching infinity, we're just talking about our x values getting really big and then dropping off the coordinate plane, or getting really big but negative and then dropping off the coordinate plane. So approaching infinity would be like that, and then approaching negative infinity would be like that. So let's look at an actual graph and let's use some of this notation to classify some of the things we're seeing. And we'll also label our asymptotes, describe these locations, and come up with actual equations to label these particular boundaries. So here's another example of a rational function. Notice it looks very similar to the reciprocal function, but the reciprocal function is centered at the origin, whereas this particular function is not. In this case, this function is centered here at the point 4, 2. So it's almost like taking the reciprocal function and then just recentering the graph at the location 4, 2. Same kind of thing. So let's use some of these notations that we just described above. So first, as x approaches 4 from the negative side, in other words, from the left-hand side, f of x, aka y, approaches what? We want to know what's it approaching. So as x approaches 4, here's x equals 4. As x approaches 4 from the negative side, in other words, as we look at our graph going from negative infinity along the x-axis toward 4, we're asking the question, what are the outputs doing? What are the function values? What are the y values doing? So in other words, imagine tracing the graph moving horizontally from left to right. what's happening to the y values as we get really, really close to 4? Well, as we get really, really close to 4, f of x, aka y, is dropping all the way down to negative infinity. The y values are getting really big, but in the negative direction. So as x approaches 4 from the negative side, f of x is approaching negative infinity. Now as x approaches 4 from the positive side, in other words, as we trace the graph going from right to left, starting at big positive numbers going towards 4, and trace the graph in that direction, what's happening to the function values, the y values? Well, in this case, they're going all the way up to positive infinity. So as x approaches 4 from the positive side, f of x, the y values, as we get really, really close to 4, are going up towards positive infinity. Now something special is happening at 4. At 4, notice on either side we're either getting really, really big and negative or really, really big and positive. 4, this location at 4, x equals 4, represents the location of our asymptote. So it's not a coincidence that we have infinite behavior around this x value at 4. The reason we have this particular behavior with our y values is because x equals 4 represents the location for our vertical asymptote. So the vertical asymptote on this graph is going to be the line x equals 4. That value around which we're seeing this particular infinite behavior with our function values. Now I want to emphasize this now. When we write an asymptote is a line, which means it's represented by an equation. So you can't just say the asymptote is 4 or it's at 4. We need the x equals part to indicate that we're talking about a vertical line. So a vertical line is always of the form x equals, every point on that line has an x value of 4. Y can vary infinitely, but x has to be 4. So x equals 4 is the only way we can represent that particular vertical line. So the x equals part going to be very important. Now let's change the notation a little bit. Instead of approaching a specific constant, what about approaching infinity? So as x approaches negative infinity, f of x approaches what? What's happening to the y values? So as x approaches negative infinity means we're tracing the graph, but we're going outwards toward negative infinity. So we're asking the question, as our x values continue to decrease, what's happening to the y values? Where are they going? Well, as our x values continue to decrease, our y values continue to get closer and closer and closer and closer to this boundary line at 2. The arrows here indicate that we can expect the same behavior further off on the graph. Even though this is all we can see of the coordinate plane, the arrows indicate that things are going to continue in the same fashion. So we continue to get closer and closer and closer to this boundary at y equals 2. So as x approaches negative infinity, f of x, the y values, the outputs, are approaching positive 2. And it's worth noting that they're approaching them from below. So we're starting out with y values that are maybe about 1.5, then maybe about 1.8, 1.9, closer and closer and closer and closer to 2. Never quite there, but we're approaching from below the y value 2. Now what about as x goes to positive infinity? In other words, we fall off the coordinate plane towards the right. What's happening to the outputs, the y values? Well, as we trace the graph going out in this direction, this would be the branch we would follow. So as we go out towards the positive x values, our y values are also approaching this boundary. Again, the arrows indicating that we see the same behavior as we fall off the graph. So the line continues, the boundary continues, and the graph continues as well, getting closer and closer and closer and closer to this boundary. So maybe we're at about, 2.7, 2.8, then about 2.5. We'll get closer and closer and closer and closer, infinitely close to the number 2. But here, as we go towards positive infinity, we're approaching this value 2 from above. So on the left-hand side, we're approaching 2 from below. On the right-hand side, we're approaching 2 from above. But what's special about the number 2, about specifically y equals 2? Well, that's the location where we have that horizontal boundary. So because we have this particular value that's being approached as our x values become infinite, the horizontal asymptote is at that location. So because it's a horizontal line at 2, its equation is going to be y equals 2. Again, the y equals part is going to be important. It tells us we have a horizontal line. Y is equal to a constant means we have a horizontal line. So x equals, y equals, don't forget those parts. Very, very important. Now it's worth talking about other kinds of things we can see from this graph. So specifically, where is the graph increasing? Where is it decreasing? What's the domain? What's the range based on the graph we're seeing for this function? Increasing and decreasing is something that you'll talk a little bit more about once you get to calculus. So for now, we can only determine where things are increasing or decreasing having been given the graph of the function. When you get to calculus, you'll determine how things increase and decrease without actually needing the graph of the function. So when we look at a graph, what does increasing mean? What does decreasing mean? Increasing means, as we're looking left to right, always following left to right, increasing means the graph is sloped upward as we go left to right. Decreasing means, as we go left to right, the graph is sloped downward. Now it's possible to also have a location where the function is constant. That would be strictly horizontal. We have an actual horizontal location on the graph. So where are we increasing? In other words, as we look left to right over the graph, we're looking for locations where the graph is sloped upward. You want to be really, really careful here. You need to forget about the arrows for a minute, because you're probably looking at this arrow thinking, okay, it's pointing upward, so I'm increasing right there. Not quite. We're looking left to right, so strictly left to right. So as you follow the graph from left to right, are there any locations where it's sloped upward as you move left to right? Well, if you follow this portion, left to right, this is entirely a downward slope. So over this particular portion of the graph, as we go left to right, everything is decreasing here. Now what about this portion? Again, forget about this arrow, pretend it's not there. As you go left to right, what's happening? Well, going left to right, this is still a downward slope all the way from left to right. So as it turns out, there's actually nowhere on this graph where our function is increasing. However, just based on what we demonstrated, we are decreasing over the entire graph, all the way from negative infinity to 4, decreasing over the intervals of the domain, not specifically saying we're starting at a y value and decreasing down to negative infinity. We're essentially tracing the domain and saying over these portions of the x values, this is where we're doing one thing, over this portion, this is where we're doing another thing, so on and so forth. So going from negative infinity to 4, we are decreasing. Now going from 4 to positive infinity, we're also sloped downward and decreasing. What about 4 itself? Well, we can't actually say anything about 4 because there isn't really any graph there. Remember, this is an imaginary line. It's a boundary. There's graph to the left, there's graph to the right, but there at x equals 4, there isn't really anything. There's actually just a big hole. There's a big gap. So we can't actually classify anything we specifically see at 4 because there isn't technically anything there. So if we're going to define the intervals where we're decreasing, we can only define it for the portions of the x-axis where we actually have function values represented. So from negative infinity to 4, and then from 4 to infinity, not including 4. So we're decreasing over the interval from negative infinity to 4, not including 4. And then we're also decreasing over the interval from 4 to infinity. Notice where else we saw 4. 4 is also the location of the vertical asymptote. Well, domain decreasing, in this case, decreasing doesn't necessarily have anything to do with that, but the fact that there's a break there at 4, this break right here, This is where we had the vertical asymptote. So not a coincidence that there's a break at that location of the vertical asymptote. And then last but not least, let's talk about domain and range. What's our domain? Our set of inputs. What's our range? Our set of outputs. So domain, very, very closely related to this idea of the vertical asymptote. Wherever there's a break in the domain, that's where we have one of those vertical asymptotes. So our graph covers all the x values from negative infinity to 4, and then we also have x values going all the way from 4 to infinity. If we trace the graph, that's the portion of the x-axis that would be covered. So our domain is going to be negative infinity to 4, union 4 to infinity. Again, that 4, the location of that 4, that break, that's where we have the vertical asymptote. Now what about the range? What y values do we cover? Well, again, we have a break in the y values, and the arrows indicate we're going to continue the same way. We're not going to touch or cross that particular boundary. We have stuff that's above it, we have stuff that's below it. So we have y values all the way from negative infinity up to 2, not quite reaching 2. And then we also have y values from 2 up to positive infinity. Again, not touching 2, not actually reaching it. So that's going to be our range. The range is going to be negative infinity to 2, union 2 to infinity. And these breaks right here. The break in the domain, that's the location for our vertical asymptote. This break in the range, that's the location of our horizontal asymptote. So all of these different things using this particular notation, not necessarily reaching a value, but getting really, really close, approaching it. These things can be determined fairly easily if we have the actual graph. So before we had this actual graph, from the graph, we can interpret everything we're looking at. We can answer pretty much any question we want. What happens if the graph is not given? Well, ideally, we'd like to be able to graph these kinds of functions. So how can you identify the locations of these boundaries? That's going to be the key part of graphing a rational function, since the boundaries are specific to these kinds of functions. So finding these boundaries, graphing those, and then getting some points is going to be our technique for graphing our rational functions. So let's talk a little bit more in detail about how we find these asymptotes algebraically. We can see them on a graph. How do we find them algebraically? Well, we already talked a little bit about how you'd find a vertical asymptote, where you find those asymptotes. So we're looking for values that make the function's denominator 0. So if c, the constant c, makes the function's denominator 0, then the line x equals c is a vertical asymptote. Again, given that we've already canceled out any common factors and our function is fully reduced. So x equals c, where c is any value that makes the function's denominator 0, that's going to be a vertical asymptote. And keep in mind, if we have a denominator where more than one value makes it 0, then we may have more than one of these boundaries. It's very possible that we have a lot of vertical asymptotes. Now, what about the horizontal and potentially slanted asymptotes? Those are going to be a little bit more complicated to find, but we essentially have a test that we can apply to determine if we have one of these, and if so, what it's going to look like. So we're going to think of our function, again, truly as a rational function, but we want to focus in on the individual polynomials in the numerator and the denominator. Specifically, we want to look at our leading terms in the numerator and denominator. We're going to compare their degrees, compare the degrees of the numerator and denominator. What does degree mean? Well, remember, degree is going to be the highest exponent. So the highest exponent in the numerator, the highest exponent in the denominator. We're going to call those n and d, respectively. So n, highest exponent in the numerator, d, highest exponent in the denominator. Now, in terms of comparing, we're determining which one's larger, which one's smaller. So suppose the numerator's degree is smaller than the denominator's degree. That could look a variety of different ways. That could be something with an exponent of 1 over something with an exponent of 2. It could be an exponent of 1, an exponent of 3, 2 and 3, something like that. Anytime the numerator's degree is smaller than the denominator's. In that case, we have a horizontal asymptote, not a slanted asymptote, and the actual asymptotes equation is going to be y equals 0, the horizontal line that passes through a y value of 0. We have a name for this. We call this the x-axis. So anytime our numerator's degree is less than our denominator's degree, we have a boundary at the x-axis, which is actually what we're seeing here with the reciprocal function. It's got that boundary at the x-axis. We can determine that from the function itself. So notice the function itself, 1 over x, well, the numerator is just a constant. So we would say the highest exponent in the numerator is actually 0. Because there's no x, we can think of it as x to the 0 power. In the denominator, we have an x. We can think of that as x to the first power. So the degree in the numerator is less than the degree of the denominator, and we fall under this case. Now, what about when they're equal? So that would be like linear over linear, quadratic over quadratic, cubic over cubic, something like that. In that case, we also have a horizontal asymptote, but it's not going to be at the x-axis. It's going to be in a different location. It's going to be y equals, because it's a horizontal line, it's going to be y is equal to whatever number we get when we take the ratio of the leading coefficients. So a sub n is what we're calling the coefficient in the numerator, and then b sub d is what we're calling the coefficient in the denominator. So these two values will be constant. We're taking them and we're dividing them. We're taking their ratio. So whatever value we get when we take their ratio, that's going to be the location of our horizontal asymptote. So y is equal to that number. Now the only other possibility, n could be less than d, it can be equal, or maybe n is greater than d. If n is greater than d, we do not have a horizontal asymptote. So automatically we rule that out. However, if we fall under the specific case where the numerator's degree is exactly 1 more than the denominator's degree, it's exactly 1 more. So that would be like quadratic over linear or cubic over quadratic. They differ by just 1 and the numerator is higher than the denominator. That's going to be the special case and the only case where we have a slanted asymptote. It's going to be a diagonal line. And when we find its equation, it's going to be an equation in slope-intercept form. So it's going to be y is equal to an expression in slope-intercept form, mx plus b. But the actual expression we're going to get from division. It's going to be y is equal to the quotient we get from actually dividing the numerator and the denominator. So y is equal to the quotient when we divide p of x, our numerator, by q of x. Now when we divide, we are going to get a remainder. We're just going to throw the remainder away. So whatever the actual quotient is, that's going to be the expression we have for the slope-intercept form of our line. Now a graph can cross a horizontal asymptote. If we have one of these asymptotes, the graph may cross it. So to determine whether or not it does, we're actually going to take the function, f of x, our actual rational function, and set it equal to whatever value we have representing the location of our asymptote. Essentially what we're doing is we're taking the two equations and we're setting them equal. We're taking the equation of the asymptote, setting it equal to the equation of the function. We're looking for values that they have in common. So we run into one of two situations. Either this equation that we generate can be solved. It does have a solution. So if it can be solved, then the solution represents the location, or the x values, where the asymptote is crossed. So we're solving for x in this equation that we generate. We solve for x. If we can solve for x and get an actual solution, those are going to be the locations where we cross the asymptote, where our asymptote crosses our function. Now, it's also possible when we create this equation and we attempt to solve it, we end up with an equation that can't be solved. If that's the case, then the graph and the asymptote do not cross. Sometimes they will, sometimes they won't. In some cases, we may not even have to set this up to solve. One time saver here is just to use your graphing calculator. So the graphing calculator can help you determine if and where any asymptotes cross your graph. So we're going to use the graphing calculator to save a little bit of time, particularly with things like this. So let's summarize everything we need to do to get our graph. Some things we always do. So for our function to graph, number one, start by finding all the intercepts. Those are always going to be good things to graph. Intercepts typically mean something in the context of an applied problem. So if we're thinking about this function as representing an actual physical situation, it's going to be important to find the intercepts because the intercepts typically have some actual physical meaning within the context of the problem. Now once we have our intercepts, we're going to graph all our vertical asymptotes as dotted lines, find all of those, graph those. We graph them as dotted lines because remember they're not actually there. They're imaginary boundaries that are splitting our graph up into pieces. Same thing for any horizontal or slanted asymptotes. Graph those as a dotted line. Now it's worth mentioning here, for our vertical asymptotes, we can have many. Any value that makes our denominator 0 represents the location of a vertical asymptote. So if there's more than one value that makes the denominator 0, there's going to be more than one vertical asymptote. On the other hand, horizontal or slanted asymptotes, you can only have one. And you can't have one of each. Only one. So if there's a horizontal one, that's it. If there's a slanted one, that's it. You're only going to find one if you find one at all. It's possible you may not have one, but if you do have one, there's only going to be one. Now, sometimes that's going to give you enough information to get a pretty good graph. In some cases, it's only going to give you information about certain portions of the coordinate plane. So if there's any region of the coordinate plane where it's still unclear what the graph may be doing, that's when you're going to need to come up with some more points. Just enough to get a sense of how the graph is shaped and then how it's oriented, how the tails are pointing in those different branches of the graph. Now this is going to be a good time to use the table function on the graphing calculator. So rather than relying on the actual image your calculator generates, it's beneficial to use the table function, which we'll talk about how you do that, because it's going to give you actual ordered pairs to graph. It's going to give you something that's accurate rather than something that you just have to look at and estimate. So let's do a few examples. We want to graph all of these. And again, if you don't have your graphing calculator out yet, make sure you have that out and then your straight edge of some type. So we want to sketch the graph of f of x is equal to negative 2x plus 4 quantity divided by x plus 2. So linear divided by linear. Let's start by focusing on that. It's a linear numerator, a linear denominator. Okay, so let's start with our intercepts. We always have the same technique for finding intercepts. So a y-intercept occurs where x equals 0. So we're going to let x be 0. Okay, if we have function notation, that means the same thing as subbing in f of 0. Which means we're going to take the rule for f and we're going to replace the inputs with 0. So negative 2 times 0 plus 4 divided by 0 plus 2. So these first two terms, numerator and denominator, those are just 0, leaving us with a positive 4 and a positive 2. Divide those, and that's going to give us 2. So our y-intercept is at 0, 2. Remember, if we find one, we'll only find one. If we found more than one y-intercept, we no longer have the graph of a function, so we'll only find one. Now for our x-intercepts, we're going to let y be 0. So that means replacing f of x, which represents y, with 0 and taking the function and setting it equal. So negative 2x plus 4 divided by x plus 2 is equal to 0. Now don't be alarmed by the fact that this is a rational equation. Because it's equal to 0, it's a little bit simpler than a lot of other rational equations. Let's think about the only ways that this could be true. If we're taking a number, so the numerator represents a number, the denominator represents a number, one number divided by another. The only way we can have two numbers divided with a result of 0 is if the numerator is 0. 0 divided by 1 is 0. 0 divided by 2 is 0, so on and so forth. What if the denominator is 0? Well, 1 over 0, remember that's undefined. That's not equal to 0. So the only way this is true is if the numerator is the value that goes to 0. So rather than having to solve this entire rational equation, we can really just set the numerator equal to 0. Any x value that makes the numerator 0 represents the location of an x-intercept. So solve for x, move your 4 over, and so we get x is equal to positive 2. So that means our x-intercept, we're only going to have one in this case, is going to be 2, 0. It's a coincidence that these were both 2. Don't think of that as a pattern. It just happened for this particular function. Now, asymptotes. This is new for our rational functions. Vertical asymptotes, horizontal or slanted asymptotes. Now, vertical asymptotes, remember those are going to occur wherever the denominator is 0. Wherever we have an exclusion from the domain, graphically speaking, that represents one of those vertical boundaries. So we can find any vertical asymptotes by taking our denominator and setting it equal to 0. What values, if any, make that denominator 0? Well, if we solve for x, we're going to get x is equal to negative 2. So that is going to be the equation of our vertical asymptote. Remember, when you write the actual equation, you need the x equals part. Don't just say the vertical asymptote is negative 2. It's the line passing through x equals negative 2. So the equation is going to be important. The x equals part is important. Now, horizontal, slanted, remember for this, we're comparing the degree in the numerator and the degree in the denominator. What's the highest exponent on x in the numerator? What's the highest exponent on x in the denominator? Well, in the numerator, it's going to be 1. This is linear, so the highest exponent is 1. The denominator is also linear, so the highest exponent is also 1. So this means that we're in the case where n and d are equal. So let's flip back over and see what that tells us. We're in the case where n and d are equal. So we have a horizontal asymptote, and its equation is going to be y is equal to the ratio of the leading coefficients, whatever those two numbers are out front in our numerator and denominator. So our equation is going to be y is equal to, for horizontal, the ratio of the leading coefficients. Well, in the numerator, it's negative 2. In the denominator, it's an understood 1 in front of that x. So y is equal to the ratio, negative 2 over 1, which means y is equal to negative 2. That's going to be our horizontal asymptote. So let's put everything we have so far onto the graph, and we'll see what we have. Try to graph these as neatly as you can. The neater it is, the easier it's going to be to interpret what we're seeing and get a good graph. So let's do our intercepts first. So we have a y-intercept at 2, we have an x-intercept at 2, and then we're going to graph our asymptotes, both at negative 2. Now as you graph these, remember you're going to graph them as dotted lines, and my recommendation is maybe graph them slightly to the side of the grid lines so that you can actually see what you graphed. Make sure you know where these actually are. So vertical asymptote at x equals negative 2, and then a horizontal asymptote at y is equal to negative 2. You may also want to graph these in different colors if that helps. Always a good idea. Okay, so that's all we have so far. We don't really have a full picture, but we do have enough information to determine a lot of different things. So these 2 points have to create a curve that, number one, is not going to pass this particular vertical boundary. Remember, nothing touches, crosses one of those vertical boundaries. So the portion of the graph that goes through those 2 points is not going to touch or cross that particular vertical boundary. Now, what about the horizontal boundary? Does it touch that? Does it cross that? Because remember, there's a possibility that we can touch or cross our horizontal asymptote. Well, here's how we determine whether or not we do without using the graphing calculator. Let's look at this algebraically. So this is the equation of our horizontal asymptote. It's a horizontal line. And this is the equation of our function. It's what we're graphing right now. We want to see if these two graphs have anything in common. If they do have something in common, then we can find the location for that common point by setting them equal. In other words, if this represents y and this represents y, then take the two other values and set them equal. Take the expression for the function, take the value representing that asymptote, and then set them equal and see if there's any x value that actually makes that true. So we're going to solve the equation, negative 2x plus 4 divided by x plus 2 is equal to negative 2. We want to solve that equation, see if we can. So we need to move our denominator over. That's always a good way to start with any rational equation. So multiply both sides by x plus 2, move that over. So negative 2x plus 4, and when we move it over, that's going to be negative 2 times x plus 2. Okay, distribute your negative 2. So we have negative 2x plus 4 is equal to negative 2x minus 4. Now we would combine our like terms. So get all your x's on one side, get all your constants on the other side. So it doesn't matter which way you go, but say we want to move left or right to left. So add this 2x, it combines over here. Notice though, these terms are like, and they're the same in the sense that it's literally the same term. So if I were to add 2x and move it over, these actually just cancel out. But what are we left with? After we do that, we're left with 4 is equal to negative 4. So our variable has gone away. There's no way to solve for x, but what we also just ended up with is a contradiction. That can't possibly be true. So that's our indication that we do not cross that line. If we had been able to find a value for x, that would represent the x value for the point where we cross the horizontal asymptote. But because we can't solve that equation and we end up with a contradiction, we do not actually touch or cross our asymptote. So what that tells me is that these 2 points, number 1, can't cross my vertical boundary, but number 2, they also can't cross my horizontal boundary. So essentially what's going to happen is we're going to have a curve passing through those 2 points that's just going to hug those 2 boundaries. It's going to approach positive infinity as the x values get closer and closer to negative 2, and it's going to approach negative 2 as our y value, or excuse me, as our x values go out towards positive infinity. So we're essentially going to have something like this, and we can verify this in a minute using the graphing calculator. That's going to be that branch of the graph. Now, that only gives us information about values to the right of our vertical asymptote, but we still need to answer the question, what's going on the other side? Well, this is going to be a good time to use the graphing calculator and use the table function. Suppose you didn't have access to your graphing calculator, what would you do now? Well, you just need some points. You need something to graph over to the left of negative 2. So worst case, you just pick some x values and plug them in. Pick negative 3, negative 4, negative 5. Plug them in, see what y values you get, and that's going to give you some actual ordered pairs to graph. So you don't actually need the graphing calculator to do this, but it is definitely a time saver. So go into your graphing utility if you're not already there. Let's clear out what we just graphed. And then we want to type in the actual function notation into the graphing calculator. So f of x, that's represented as our y, that's already there. We want to type in the actual expression. Now when you type a rational function, make sure you put parentheses around the numerator and put parentheses around the denominator. That's going to be very, very important. If you leave them off, you might want to actually have a variable, Let's try that again. So negative 2x, there we go, plus 4, close your parentheses, divide by x plus 2. Now, if you leave the parentheses off, what your calculator thinks you want is to divide just the 4 and the x, just the 2 things that are right next to each other, and then add on a negative 2x and add on a 2. That's not really what this function is saying. you actually need to have the parentheses in order to indicate that each of these is considered to be a factor and we're dividing the entire factor. So now let's graph this. There we go. So that verifies number 1 on the right hand side. It looks like our graph looks pretty good. We can verify where those intercepts are in just a minute. And it also gives us a sense of what the other portion of the graph is going to look like. But ideally, we'd rather get some actual points instead of trying to just ballpark what this is going to look like and sketch it roughly. So one good option is to use the table. Notice it's right above graph in blue. So I'm going to hit second and graph, and it's going to bring me into the table. Now I can do several different things here in the table. Number 1, I can verify the location of pretty much everything I've already graphed. So let's start with the intercepts. We have an ordered pair at 0, 2, okay, and that's verified. And then we have an ordered pair at 2, 0. That's also verified. So our intercepts look good. Now what about that vertical asymptote? Believe it or not, we can see that as well. It's at x equals -2, so let's scroll. And notice there at x equals -2, you see an error. Anytime you see an error, it means that the output is undefined for that particular input. Well, in this case, an output being undefined is represented by this vertical asymptote. So that verifies the location of our asymptote. Now, you're not going to see an individual value that verifies the location of your horizontal asymptote, but here's a way you can verify that as well. So remember, it's at y equals -2. Let's see what happens as we continue to scroll. I want you to follow the x values and see what's happening to the y values as we continue to scroll. Notice as the x values get more and more and more negative, the y values are getting closer and closer and closer to -2. They're not going to quite get there, but the further out we scroll, the closer and closer we get to -2. That's going to be a confirmation that this is the location of our asymptote. The fact that we're just tapering off and our y values are getting closer and closer to this one value, slower and slower and slower, that's our indication that that's our asymptote. And we can see the same thing in the other direction if we were to scroll in that direction as well. It'll be approaching -2. So same kind of thing. Notice we're approaching -2, but now we're approaching from the other side. We're approaching from above. Okay, so that's how you can verify your horizontal asymptote. Now what we really want from this table though is some information about everything that's to the left of that vertical asymptote. So we want to know what's happening past -2. Let's get some other points. So this table tells us that at -3, when x is -3, y is -10. So that's another ordered pair that we could graph. Okay, let's scroll a little bit more. -4, 1, 2, 3, 4, 5, 6. Okay. You don't have to graph ones that are difficult to graph. Graph what seems easy to graph, assuming you have your choice of points. And ultimately, you really just need enough to get a sense of the shape. So there we go. So that shows us the general shape of our curve. Remember, we never cross the vertical boundary, and we already verified that we're not going to cross the horizontal boundary. So that means that we have something that looks roughly like that. So that's going to be our general graph. Notice these two branches are mirror images. If we were to think of this as the center of our graph, these two branches are going to be mirror images across that particular center. And last but not least, now that we have a graph, let's identify the domain and range for this function. So what x values do we cover? Well, we cover everything from -infinity up to -2, and then everything from -2 to positive infinity. So there at that vertical asymptote, that's where we have a break. So our domain is -infinity to -2, union -2 to positive infinity. And again, that break, that's a break in the x values, and that occurs where we have our vertical asymptote. Now what about the range? We also have a break at -2 in the y values. So we have y values below that, we have y values above that, but we don't have a y value at -2. So our range is also -infinity to -2, union -2 to infinity. Now I want to emphasize again, The fact that these two values are the same is just based on the fact that we have a particular function where those values both occurred. But don't try to infer any pattern from seeing that. It's not necessarily going to be the same. If we had asymptotes in other locations, those values would not necessarily be the same. So there is no specific pattern there. Okay, let's look at another example. Okay, now we have a linear numerator and a quadratic denominator. So let's find our intercepts, let's find our asymptotes, and let's graph it. So for our y-intercept, we're going to let x be 0. So evaluate f of 0. So our numerator is going to be 4 times 0. Our denominator is going to be 0 squared minus 4. Now be careful when you simplify this. The numerator simplifies to 0. The denominator simplifies to negative 4. Well, 0 divided by negative 4 is going to be 0. So the ordered pair 0, 0 is going to be our y-intercept. Now notice 0, 0, the origin, is also an x-intercept. So when we look for our x-intercepts, this will be one of them. It's possible we could have more than one x-intercept, but we know for sure this will be one of them because the origin is both an x and a y-intercept. So for our x-intercepts, we're going to let y be 0. In other words, we're going to take our function and set it equal to 0. So 4x divided by x squared minus 4 is equal to 0. Now, as we discussed with the previous one, number divided by a number is equal to 0. The only way that's true is if the numerator is 0. So that's the same thing as setting 4x equal to 0. Divide your 4, which means x is equal to 0. So we also get the ordered pair 0, 0 here, and we didn't find any additional intercepts. So if the only intercept we have is at the origin, this means all the other points on the graph have to be located somewhere within a quadrant. Those are going to be the only, or that's going to be the only location where we actually touch or cross an axis. So that is something to keep in mind as we graph. That's going to give us information about the shape of the graph. Now, vertical asymptotes, do we have any? Anything that makes our denominator 0 is number 1, excluded from the domain, and number 2, it represents the location of a vertical asymptote. So we're going to take our denominator, set it equal to 0, and then we want to solve for x. Now you could factor this is a difference of squares, or because it's only one term involving x, we can also use the square root property and just isolate x and solve that way. So add the 4, move it over, so x squared is equal to 4, and then we have to take the square root of both sides. Now remember, whenever we have an equation and we take a square root, we need plus minus on one side, typically the numeric side, at least in a case like this. So x is equal to 2 and x is equal to negative 2, two different values. That means we actually have 2 vertical asymptotes. So one has an equation of x is equal to negative 2, and one has an equation of x is equal to positive 2. So we actually have 2 vertical boundaries on this graph. Well, if one boundary splits the graph into 2 pieces, then 2 boundaries are going to split the graph into 3 different regions. So we're going to have 3 different branches once we actually graph these asymptotes. Okay, horizontal or slanted. Remember, now we're comparing the numerator and denominator. What's the degree of each? Well, the numerator is linear. It has a degree of 1. The denominator is quadratic. It has a degree of 2. So we're in the case where n is less than d. So what does that tell us about our asymptote? We're in this case where n is less than d. So we have a horizontal asymptote, specifically at y equals 0, otherwise known as the x-axis. So our asymptote is going to be y equals 0. So we have 1 horizontal asymptote, 2 vertical, and then 1 common intercept. So let's put all of that onto our graph. So intercept at the origin, okay, and then we have a vertical asymptote at negative 2. Remember, graph it as a dotted line, not really there, imaginary. Okay, and then we also have a vertical asymptote at positive 2. And so already we can see that divides the coordinate plane into 3 regions, so we're going to have 3 branches of our graph. And then we also have our horizontal asymptote. I'm going to graph it slightly above the x-axis so we can actually see it. Make sure you graph it in such a way so that it's not directly on the axis so you can actually see the line. There we go. So here's a question. Does our graph cross the horizontal asymptote? Well, in this case, the answer is yes. Notice we already have a point crossing the asymptote. It just so happened that our horizontal asymptote coincided with the x-axis, and we already determined that we do have an x-intercept. So this is going to be the location where our graph actually does cross our horizontal asymptote. Now, we're still left wondering a lot of things. Now we technically have 4 regions. So the asymptotes, the vertical asymptotes, are going to break the coordinate plane into 3 regions. But now this intercept also breaks the middle region into 2 separate parts. We need to know what's happening on either side of that intercept. So to the left of the intercept, are we above? Are we below? To the right, are we above or are we below? Those are questions that both have to be answered. So there's actually 4 separate regions where we potentially need some additional points in order to get a good graph. So we don't know what's happening in any of these 4 regions. I'm going to mark them so we know to check all of those different locations with the graphing calculator. So let's go back in, clear out your graph, and then we're going to type in our function 4x over x squared minus 4. Again, make sure you have your parentheses. So 4x in parentheses divided by x squared minus 4, also in parentheses. Okay, so once you're satisfied with that, hit graph, and that's going to give us a good picture. We have a sense of where things are going to be. Let's get some actual ordered pairs from that graph. So go into the table function, second, and graph, and there's our table. Okay. So let's start in the center. Let's verify, number 1, that our intercept is correct. Okay, there we go. So at x equals 0, we have y equals 0 as well. So we do have that intercept at the origin. Now what's happening on either side of that intercept? Well, to the left, at x equals -1, we have y is 1 1/3. So at x equals -1, y is 1 1/3. And because that's between the grid marks, just ballpark it. When x is 1, y is -1 1/3. And once we have these 2 points, we now hug these asymptotes. Keep in mind, this is the only location where we cross the x-axis, which means everything that goes through this point has to stay above, and everything that goes through this point has to stay below. So we end up with a shape that looks something like that. And then we also want points to the left of our leftmost asymptote and to the right of our rightmost asymptote. So something smaller than -2, something greater than +2. Well, -2, there's the error. +2, there's the error. That verifies the asymptotes. At -3, when x is -3, we're at -2.4. So -3, -1, -2, about -2.5. At -4, we're at -1 1/3. So -4, -1 1/3. And then so on and so forth. Again, we don't cross our horizontal boundary again because this is our only intercept, and we never cross the vertical boundary. So that means we're just going to follow those asymptotes as our x and y values become infinite. And then on the other side, when x is 3, we're at 1, 2, 2.4. Then when x is 4, we're at 1 1/3. Notice there's some symmetry in the y values in this case. We had the same y values except for differences in sign. Not a coincidence. We do see a lot of symmetry with these kinds of functions. And so that's going to be roughly what that looks like. And that is confirmed by our graph on the calculator as well. That's roughly the shape we expected to see. Now what about the domain and range? Domain is broken up by our asymptotes, so we have discontinuities at -2 and 2. So our domain is going to be all real numbers except those values. So -infinity to -2, union, -2 to 2, union, 2 to infinity. 3 regions. So we have 3 intervals in our domain, 3 regions, 3 branches represented on our graph. Now what about the range? Remember with the previous example, the horizontal asymptote represented a break in our range. Does that actually happen here? Well, on the left-hand side of the graph, far left, it looks like the y values are capped at 0, so we have negative y values, -infinity up to 0, not quite to 0. On the right-hand side, we have everything above, also not reaching 0. But notice that branch in the middle. That branch in the middle is continuous all the way from -2 to 2, and the y values span all the way from -infinity to infinity, and we do actually have a location where we cross over and hit y equals 0. So in this case, because of that central branch, we don't actually have a break in the range. We do actually cover all real numbers. So our range is going to be all real numbers. So slightly different graph. Why did we end up with a different graph here? These two branches look kind of similar to what we saw before. This one's very much different. The biggest difference here is the fact that we went from a linear numerator and a linear denominator to now having a quadratic denominator. The more complicated the individual functions get, the more complicated the graph is going to be and the more interesting features we're going to get on our graph. So let's do one additional example. Okay, now we have a quadratic numerator and a linear denominator, so we've switched them. So let's start with our y-intercept, evaluate f of 0. So f of 0, we're plugging in 0 to our numerator, plugging into our denominator. Okay, and our denominator is 0 minus 2. Okay, so 3 terms are 0. What are we left with? Be very careful with your signs here. The numerator is -12. The denominator is -2. Those negatives become a positive. So we have a 6. So our y-intercept is going to be the point 0.06. Now what about x-intercept or intercepts? We're going to take our function, set it equal to 0, let y be 0. And then as we've discussed, the only way that ratio evaluates to 0 is if our numerator is 0. So I can also just take the numerator and set that equal to 0. Since this is quadratic, we do have to factor it in order to solve. So we want numbers that multiply to give -12 that also add to give -4. So that's going to be -4 and +3. And so when we solve for x, x is going to be -3 and x is going to be +4. So we found 2 x values here. That means we have 2 x-intercepts. So we have an intercept at -3, 0, and we also have an intercept at 4, 0. So in this case, we have 3 intercepts rather than having 2 or 1. Vertical asymptotes, do we have any? Anything that makes that denominator 0, that's a vertical asymptote, location for one. So take your denominator, set it equal to 0, and we get x is equal to 2. So the equation of our single vertical asymptote is going to be x equals 2. And then what about horizontal or slanted? So we're comparing the numerator, the denominator. The numerator is quadratic, so its degree is 2. And then the denominator is linear, so its degree is 1. So in this case, n is greater than d. So automatically that means we do not have a horizontal asymptote. But also notice that n is exactly 1 more than d. So we fall under that special case. If n is exactly 1 more than d, it's It's higher, but it differs by exactly 1, and we have a slanted asymptote. So y is going to be the quotient we get when we actually treat the function as a division problem. Divide the numerator by the denominator. Now, because our denominator is linear, we could actually do this division with synthetic division. But suppose it were cubic and quadratic. Well, something like that, we wouldn't be able to use synthetic division. We'd have to use long division. So just for sake of the practice, let's do this division with long division. So we have x minus 2, and we're dividing it into x squared minus x minus 12. Okay, so the first two terms I'm dividing are x and x squared. So x squared divided by x gives me x, so that's going to be the first part of my quotient. Multiply and bring it down, so x times x is x squared, x times negative 2 is negative 2x, and then we're subtracting all of that. Our first terms reduce to 0, which is what's supposed to happen, and the negative x, watch your signs, negative x plus 2x is going to give me a positive x. And then I'm going to bring down whatever's left, in this case a negative 12. So now I'm dividing x into x. So x divided by x is equal to 1. It's the next part of my quotient, positive 1. And technically speaking, I can stop there. We're going to disregard the remainder, but for the sake of finishing it, let's finish it. So 1 times x is going to be x. 1 times negative 2 is going to be negative 2. And then we're subtracting all of that. So again, the first terms reduce to 0. And then we have negative 12 minus negative 2, so plus 2. Negative 12 plus 2 is going to be negative 10. But again, we throw that away. We don't need it. All we need is this quotient. So notice this is in the form mx plus b. This is in the form we would get if we were going to write a line in slope-intercept form. So the equation of our slanted asymptote is going to be y is equal to x plus 1. So we have 3 intercepts, 1 vertical asymptote, and in this case we had a slanted asymptote. So let's put all of that on our graph. So y-intercept at 6, and then 2 x-intercepts, 1 at negative 3 and 1 at 4. Okay, vertical asymptote at x equals 2. Okay, and then a slanted asymptote defined by the equation x plus 1. Sorry, I didn't move that up. X plus 1. There we go. Now, to graph the slanted one, you will definitely want the straight edge, even if you haven't been using it before. So because our equation is in slope-intercept form, we graph using the y-intercept and then find another point using the slope. So we have a y-intercept at 1. I'm going to put just a little dot there. Remember, there isn't technically anything there. This is going to be on that boundary line, but we do need that point in order to be able to graph that line. Now the slope is 1, so rise over run, 1 over 1. So rise 1, run 1, rise 1, run 1, and then so on and so forth. So we need to connect those dots, try to do it as neatly as possible. And again, remember, there's not really anything there. It's really just a boundary. It's an imaginary boundary. And so we connect those dots with a dotted line. And that's what we have so far. Okay. So in general, technically, we know what this graph is going to look like just based on having these boundaries. I don't know that I've ever actually seen a function that crossed a slanted asymptote. Technically, I feel like it could. Don't quote me on that. But in this case, let's look at the graph just to verify what's going to happen. We know we can't cross that vertical boundary, but what's happening around that diagonal boundary? Let's get some ordered pairs and let's see. So go back in, clear out what you just graphed, and let's type in this function. So parentheses, x squared minus x minus 12, close your parentheses, divided by parentheses, x minus 2, close your parentheses, and then we'll graph it. Notice you can't see that diagonal boundary. You're not going to be able to see it. But what would happen if we typed that in? So let's actually type an additional equation in here. So don't clear anything, but let's type the additional equation that we have for our asymptote, x plus 1. And let's graph that. Notice you can see that it's going to sort of inform the shape of that curve we already graphed. The curve we already graphed follows the shape of that particular diagonal line. That's a pretty good confirmation that that asymptote is correct. Now, we want to go into the table and just be aware you're going to see two y values. The first one is associated with the actual function. The second one is associated with that diagonal slanted asymptote. So second and graph. There we go. Okay. So let's get some ordered pairs. We can verify the ones we have already, so let's do that. So we had supposedly an ordered pair at -3, 0. Okay, so that's there. That's confirmed. We had a pair at 0, 6. Okay, that's confirmed. There's our error at 2, so that's that vertical asymptote. And then we also had an ordered pair at 4, 0. So everything we have on the graph so far checks out, including that diagonal asymptote. So let's get a couple more ordered pairs in each of the regions. So to the left of our vertical asymptote, to the left of 2, when we're at x equals 3, we have, or excuse me, to the left, so we want the other side, so 1. 1, and then 10, 11, 12, something up there. And then, let's see, we have 0, we have -3, -2, 1.5, so about right there. And then so on and so forth. If that feels like it's enough, if you have a sense of what the shape is going to be, which we should from already looking at the graph, then we can just connect those dots, and that's fairly accurate. Okay, and then the other side, so anything beyond 2. So 3, -6, 1, 2, 3, 4, 5, 6. And then we already had that intercept. 5, 2 2/3. So 5, 1, 2, and then 2/3. See if we can get some other things. Anything else? 7, 6, that's an easy one to graph. So 7, 1, 2, 3, 4, 5, 6. And then so on and so forth. Following the shapes that those asymptotes give us. And that's going to be our graph. So notice all three of these graphs that we generated were all pretty different. They had some things in common, they have features in common, but the shapes are pretty different. We can see some pretty exotic graphs once we start to take these rational functions and make the numerator or the denominator more complicated. But when in doubt, we go back to our intercepts, we go back to our asymptotes. As long as we can find these key features, then we can graph pretty much any rational function.